Yeah, so Rui, all this work was so exciting, and this is pretty much in line with some of your findings, and especially how language models could be really exciting for key phrase extraction and generation. So there's no doubt that transformer-based pre-trained language models like BERT has shown tremendous performance in NLP tasks and has totally reshaped the field. But why do they really work so well? Okay, I think it has immense capability to learn syntactic and semantic nuances of language and learn very rich representations in different modalities. And why not? And this is a picture of my daughter, and as you can see, she is using mass language models to learn words. Now, pre-training these models on large corpus has shown awesome results. Like pre-training on a huge corpus can learn universal language representations and help with several downstream NLP tasks. Pre-trained language models provides better model initialization, leading to better generalization performance and speeds of convergence on target task. And then pre-training can be regarded as a regularization that helps in avoiding overfitting on small data sets. Now, we recently actually looked into language models and attempted at actually training key phrase language models, which are also available in the Hugging Face Hub. We'll talk about that later. But the major questions that we had in our mind that is that can we formulate a pre-training objective for language models that can learn better representation of key phrases? And does learning rich representation of key phrases in a language model lead to performance gains for the tasks of course, key phrase extraction and generation? And it is intuitive that identifying key phrases can benefit many other tasks such as NER, question answering, summarization, relation extraction. Therefore, we also wanted to see if learning rich key phrase representations also aid other fundamental tasks in NLP such as NER, QA, RE, and summarization. So driven by these questions, we came up with two large language models with novel pre-training objectives that enables them to learn rich representation of key phrases. And these objectives are mainly, the KBIR objective and the KeyBART objective. So the KBIR is an encoder model suitable for the task of key phrase extraction, and the KeyBART model is a generative model suitable for the task of key phrase generation. And both of them are available in Hugging Face Hub for you to download and try them out. Now let's first look at the KBIR model. So KBIR model, as you can see, let's actually try to understand this. So KBIR model jointly learns from three different pre-training objectives. One is the mass language modeling, which is mainly implemented using token masking, then key phrase boundary infilling, which is basically doing key phrase masking, and I'll be talking about that in detail, and then key phrase replacement classifications, which helps in doing contrastive learning. And it is built on top of Robata. So in token masking, random tokens are masked and the model is asked to predict these masked tokens. This is simply borrowed from Robata's masked language modeling strategy. So this is pretty simple. Now there's another objective, and now let's talk about key phrase masking, which is going to be really interesting. So we wanted to mask key phrases, in order to learn their rich representation. But masking it could be done in a few different ways. So we initially masked it using similar to SpanBART, which already learns representations of randomly selected strands, and this looked perfect for key phrases as they are essentially text strands, but we did not get good results. One of the reasons could be that although SpanBART was learning span representations, but what essentially they were trying to do is to correctly predict the tokens inside the span with the representation of the boundary tokens, which did not look right for key phrases as they are cohesive set of words that are meaningful when put together in a given context. We were then very inspired by the text infilling task of BART, which was also trying to generate the spans of text from a single mask token. But text infilling was never implemented in the encoder setup. So we had to do that, which led to the key phrase boundary infilling objective. So in this the key phrase boundary infilling objective, essentially, we actually implement the text infilling in an encoder setup and replace the entire spans in this case, a key phrase with a single mask token. And we then try to predict the original tokens using positional encodings, embeddings in conjunction with the boundary tokens. But this is more challenging than Spanbert's objective of individual mass token predictions, as the model must predict how many tokens corresponds to a span. Now, different from Spanbird, which does not penalize incorrect predictions of a sequence of tokens within a mask token, we propose a cumulative loss across all the tokens in the mask span to capture intra-span token relationships and to learn better span representation, especially key phrase representations. This is what the key phrase boundary infilling objective does. And it takes the boundary tokens and the boundary position embeddings of the span key phrase which has been masked out and try to predict it using key phrase boundary infilling objective, which also and simultaneously it also tries to predict the number of tokens in that span. Then the other part, we also added the key phrase replacement strategy where we replace a randomly selected key phrase by selecting it from a fixed vocabulary of 500,000 key phrase. So we randomly selected like another key phrase, we which we replaced with the randomly selected key phrase for the input text. And we asked then the model to do a binary classification of whether the span is replaced or key phrase or not. And this helped us to leverage the power of contrastive learning that really helped a lot. Finally, we learned the key phrase language model by optimizing or jointly optimizing the joint loss, and we named this pre-training objective the KBIR objective. Now um, we also implemented another pre-training strategy on top of BART. Now, as we know, BART generates sequences of different lengths from the input perturbed with mask tokens along with token addition and deletion. On similar lines, we propose learning rich key phrase representations using a model called KeyBART. So in this KeyBART, what we do is that we perturb the original text and we actually do the same strategy of masking out tokens and then key phrases and also replace key phrases. And this leads to a noisy text. And what we do is that we use the current BART model and then we try to actually we generate the key phrases which are associated with the input text in the catch sequence format. And then in order to have a fair comparison with the current BART setup, what we did is that we trained another model, which instead of generating the key phrases in the catch sequence format, also generates the original input text. So this was the experimental setup. So for all our experiment, we used the large OAGKX corpus, which has like 23 million scientific articles from various domains, along with their key phrases associated. And this is very much in line with how Wikipedia has been used as corpus and how the concepts already tagged in Wikipedia has been used for pre-training, multiple pre-training tasks. So overall, we showed quite an improvement in the key phrase extraction results on 3 different data sets using KBIR. And we also overall showed very good improvements in the key phrase generation over multiple data sets. So one of the interesting things we started to try out and we hope to do more on that is that we didn't actually fine tune the KeyBART model. And then we directly did zero-shot learning on top of these evaluation data sets. And we did see a massive gain in the results in the inspect corpus, but we did get reasonable results in the other corpus. I think this is very interesting to look at, and we are very excited to try out more experiments related to cross-domain key phrase generation as well. So we also performed our experiments for standard NER data sets and relation extraction data sets and achieved near state-of-the-art results, and also for question answering, and so for summarization. So I also want to just point to another concurrent work which recently came out, which looks at resource constraint key phrase generation, and this trains a key phrase generation model in a resource constraints training, and they basically also look at introducing new pre-training objectives, which is salient span recovery and salient span prediction. So in salient span recovery, they select the spans using a TF-IDF strategy and then masks them. And then they use the BAT model to recover the mask spans during training. And in the salient span prediction, they use the same spans which they identified using TF-IDF, and they mask them and then try to generate these spans out during the training process in the cat-seq format. And this is very much similar to what we also did, and so this also actually gave reasonable results in cross-domain and key phrase generation and key phrase generation in resource constraint settings. So I think that's it for me. And now I think we'll move to Florian.